Have you ever looked up at a solar panel on a roof and just wondered? How does that silent, flat rectangle turn pure sunlight into the actual electricity that charges your phone or powers your lights? Well, today, we're going to pull back the curtain on the incredible physics that makes it all possible, taking you from a single particle of light all the way to the outlet in your wall. So here's our game plan. We're going to start with sunlight itself. Then we'll zoom way down to the atomic level to see what's really going on inside a solar cell. And from there, we'll zoom back out to see how all that tiny science comes together to power your entire home. It's a pretty cool journey, from the sun to the cell and finally to your socket.
All right, let's dive right in with Section 1, Sunlight's Secret Power. Because before we can even begin to understand the panel, we have to understand its fuel source. We're about to go from a simple sunbeam all the way to usable electricity.
This is the big question, isn't it? It honestly feels a little bit like magic. There are no moving parts, there's no noise, no exhaust. It just sits there, soaking up the sun. But what's happening inside is some of the most elegant physics you can imagine.
The key here is to stop thinking of sunlight as just a warm glow. You gotta picture it as a constant, non-stop stream of tiny, energetic particles of light. These particles are called photons, and they've traveled 93 million miles through the emptiness of space just to slam into your rooftop. And every single one carries its own little packet of pure energy.
So the sun is basically firing these little energy packets at us. But what happens when they actually hit? Well, to answer that, we need to zoom in, way in. Welcome to Section 2, inside a solar cell. This is the absolute core, the building block of any solar panel.
At its heart, a solar cell is just a very thin wafer of material. And that material is usually silicon. Yep, this same stuff that makes up sand. But this isn't just any old silicon. It's a special type called a semiconductor. And that unique property is exactly what makes it the perfect little engine for our solar panel.
So a solar cell is really a sandwich made of two slightly different layers of silicon. One layer, we call it the N-type, is specially treated so it has a bunch of extra electrons just hanging around. It's negatively charged. The other layer, the P-type, is treated to have a shortage of electrons, which creates these little empty spots, or holes. Think of it like one side has too many people and the other side has a bunch of empty chairs.
Now, when you press these two layers together, something amazing happens right at that border, that junction. The extra electrons from the N side immediately jump over to fill the empty holes on the P side, but only right where they meet. This tiny shuffle of charges creates a powerful, permanent electric field, and you can think of this field like a super steep, one-way slide for electrons. Once they go down it, it's really hard to climb back up.
That electric field, that one-way slide, is the critical piece of the puzzle. And it brings us right to the main event in Section 3, the photovoltaic effect. This is it. This is the scientific secret sauce that actually creates electricity from light.
The name itself tells you everything you need to know. Photo means light, and voltaic is all about voltage or electricity. So the photovoltaic effect is simply this incredible natural process where a material can convert particles of light directly into a flow of electricity. No middleman needed.
So here's how it works, broken down into 3 steps. First, that photon we were talking about, after its long 93 million mile journey, bam, it slams into a silicon atom inside the solar cell. Second, that photon transfers all its energy to an electron, knocking it completely free from its atom. It's like a cue ball in pool, hitting the rack and sending one ball flying. And third, that newly freed electron is now buzzing with all the energy it just absorbed from that photon. Okay, so photons are knocking electrons loose all over the place inside our solar cell. We've got a ton of energy, but right now, it's chaos. It's just a random swarm, and chaos is not electricity. To get electricity, we need an organized flow. We need a current. And that's our whole goal for Section 4, making electrons flow. Remember that one-way slide we made, that electric field at the PN junction? This is where it becomes the hero of the story. That built-in field acts like a traffic cop or a director. It grabs every single one of those free-floating, chaotic electrons and shoves it down that slide, forcing them all to travel in one single, unified direction. It brings order to the chaos.
And that organized one-way march of electrons, that is exactly what we call an electric current. It's that steady flow of charge that we can actually capture and use to do work.
At its most basic level, the interaction is just beautiful.
One tiny particle of light comes in, and it frees up one single electron. It's a perfect little exchange of energy happening at the atomic level.
But that's just one photon and one electron. Now let's scale that up. The sun is bombarding that panel with trillions upon trillions of photons every single second. Each one frees an electron, and that electric field we built, it's directing them all down that slide, creating a massive, powerful river of electric current.
So we've done it. We've created this powerful river of electrons inside the panel. Now it's time to zoom back out for our final section, powering your home. How in the world do we get that current from the roof down to your blender?
Well, there's one last really important step. The electricity that flows out of a solar panel is a steady one-way street. We call it direct current, or DC. But our electrical grid, and pretty much every appliance in our homes, they're all designed to run on alternating current, or AC, where the flow changes direction back and forth. You could say they speak two different electrical languages.
So what do we need? We need a translator. And that translator is a device called an inverter. It's really the unsung hero of every solar system. Its only job is to take that smooth, direct DC power from the panels and convert it, or invert it, into the alternating AC power that your home can actually use.
And there you have it, the whole journey from start to finish. Step 1, sunlight hits the panel, which uses that awesome photovoltaic effect to create a DC current. Step 2, that current flows to the inverter, which translates it into usable AC power. And finally, step 3, that AC power flows into your home's main electrical panel, ready to power everything from your lights to your laptop.
When you really stop and think about it, it's pretty profound. This entire elegant process, which is a direct application of quantum physics, is just silently and cleanly working away on rooftops all over the world, every single day the sun is out.
And that kind of leaves us with one final exciting thought. We've managed to master this beautiful piece of physics to harness the power of a star that's 93 million miles away. So the question isn't really how it works anymore. The real question is, now that we have this incredible foundation, what comes next? What new materials and new efficiencies will this technology unlock? The future is, quite literally, looking very bright.